Hi everyone. So this will be, a somewhat different talk. So this isn't going to be me giving you a presentation about my research. Rather, I'm going to, in effect, do some advertising for nanoHub, who's graciously agreed to host this. But I also, along the lines of that great introduction from Kaylee, I'd like to show you how we've kind of made a simplified tool where you can go from PowerPoint chemistry to making the nice spectra and field plots that that were calculated by George and Bjorn, who really know how to do these things, but in a way that's completely graphical, user interface driven, and very simple and fast. And so people who are kind of non-experts in theory can get ballpark estimations of what their fields would be and what their spectra they expect from their structures just by drawing objects and then applying some algorithm that's kind of known in the literature. So just to give you a bit of background, my name is Jeremy Smith. I'm a fifth-year graduate student in Prashant Jain's lab at UIUC, who, again, to all of you who he knows, apologizes that he was unable to be here today. But my research, to tell you why I'm interested in this, is similar to, as Bjorn was talking about, using dark field microscopy of individual nanostructures. But instead of applying these to biology, I kind of study sort of material synthesis, templated replacement type of reactions on these individual nanoparticles. And then I use the plasmon, specifically the spectra, as well as the intensities as a sensor to learn something about the materials transformations and their dynamics in solution. And so again, I really need to be able to combine these single particle spectroscopy with simulations to really gain an appreciation for how the dynamics proceed. And so the tool that we describe is based on one of kind of the two popular ways of getting these spectra and fields. There's sort of two competing methods, and different people have their own favorites, but the one that we chose to implement on nanoHub is what's called the discrete dipole approximation. And the reason we chose to do this is because it's actually pretty simple and pretty hard to go wrong when you're doing this. So what you start with is just a three-dimensional object that I've shown here that you can generate using a graphical drawing program. You then discretize that three-dimensional object into a set of points, and then you're going to describe each one of those points as a dipole. Then you're going to apply an electric field to that array of dipoles, add the fields of the individual dipoles, and then solve this in a self-consistent manner to generate spectra and electric fields. And as Bjorn and George mentioned earlier, when things get really, really small, we're always in this approximation kind of using bulk dielectric functions. And so if the dielectric function is no longer your bulk dielectric function, for example, something gets very small, or if your gaps are very, very small, and you have kind of quantum tunneling effects, then of course this approximation isn't going to be valid. But because this is so simple, we kind of, it's really easy to integrate in a really kind of user-friendly way to generate these nice field plots in the spectra. And so I'll say this code has been available for a long time. It was popularized by Drain and Flatow. It's a Fortran 90 code, and it has a few built-in shapes, but it doesn't really have a general way to make any arbitrary structure that you want and then discretize it. And what else is lacking is it doesn't really have a GUI for visualizing the structures that come out of it. And so what we've done on nanoHub is we've integrated a graphical target generation with the Drain and Flatow code and with a visualization interface for the output. And also, since this is run at Purdue through nanoHub, they have big clusters of computers, and this code actually parallelizes very well by just submitting different wavelengths as individual calculations. And so you have free access to clusters through this. So even if you kind of know how to generate your own shapes and want to do DDA calculations, you can take advantage of nanoHub at least to kind of take advantage of the computational power that's provided there for free. So the rest of this talk, hopefully this... Oh, what's happening? Oh, why am I not? Oh, here we go. Yep, okay, good. Okay, so this is nanohub.org. This is the website where all of this is implemented. We strongly encourage you to create your own account. You can use your regular Google account to log in. there's a whole bunch of tools under this resources tab. And again, I'm just going to be talking about this one specific tool which uses an implementation of the DDA code. There's many, many, many tools for many, many different applications. And another part of this workshop is to kind of encourage people who are more theoretically inclined to help in tool development on this website. So the next session, driven by my CS colleague, will be talking about how you could potentially put your codes available for other people, install them on these servers at Purdue, and then give everyone else access to easily use your codes. And they have a kind of built-in visualization backend that you can then make it easy for people to visualize the results they get. So if I go to this Tools tab, then I'll see under, going all the way down, DFT, there's a whole bunch of stuff. But DDSCAT, there's this tool called nanoDDSCAT Plus, and this is the tool that I'll be kind of talking about here. And so the way this workflow works is first we have the shape generation, which uses this openly available it's actually an animation software called Blender, but it's quite nice because you can generate three-dimensional objects with well-defined sizes easily, like for free, without completely redesigning everything. And then we can interface this kind of with our own scripts to make everything easier. So when you open it up, you'll see this is what you get. It always inputs a cube here. And then it's showing you these three axes here, these X, Y, and Z axes. And you see what else we've done is we've included these drawings here that tell you the propagation direction of the light that's going to be applied, as well as the field polarization. And so this allows you to, for example, if you want to use linearly polarized light along a particular axis of your object, you'll just know from looking at this interface exactly how your object is oriented relative to the light. So I'll just delete this and then say, getting used to using Blender can be a little bit weird at first, but it's actually quite easy, and there's a whole lot of online tutorials, which is kind of one of the reasons why we chose Blender to do this drawing. But there's a whole set of really kind of useful built-in shapes. And so what I'm going to start with here first is a cylinder, because what I'm going to do is essentially simulate a gold nanorod and then convince you that the results you get kind of make sense. So when I clicked add the cylinder here, you see, yes? Oh, sorry. Oh, sorry. Yeah, sure. No, absolutely. And like I said, come and talk to me after, and I'll totally do this. So if you log in, you go to Resources, and then go to Tools, okay? And then under Tools, go down to DDSCAT, okay? And then under DDSCAT, there's nanoDDSCAT Plus. So the plus basically just means that this includes the graphical target generation. The other one is just basically the traditional drain and flat tile code that only has their limited built-in shapes. So you want to use the plus one because that has the graphical drawing. Probably the easiest way to log in though is you can just use any Google account, and it will take that as a login on NanoHub. Getting there? So under Resources, and then Tools, and then that will bring up this menu, and then you just want to scroll down under Tag to DDSCAT. Okay? No, absolutely. This is the whole point is, and feel free to come up to me after and ask me about this. So now when we launch this tool, we'll open this Blender. So I'll give you the kind of the easiest tips for Blender that will help you with all of this. So basically, you want to use a mouse because the middle button in Blender is going to control your view. So if you hold down the middle button and scroll around, that will control the way that you're looking at your object. And then if you left click, it'll talk about some position. And if you right click, you'll be able to select an object. And every time you select an object, it will draw these arrows. And what you do with these arrows basically is you can just drag the object around in space along one of these three axes using these arrows. Now, the second important thing about Blender is so there's two modes basically that you switch between using Tab. So if you hit Tab, it will switch from moving objects around to changing the shape of objects. So now what I can do is pick a vertice and then similarly drag the vertice using the arrows or even just like free-forming. And then I can, alter the shape of my object. And I can, like, in this edit mode, I can hit delete, for example, and then delete one of the edges. And then I could make, I could connect like these different things with some new face here. So this is kind of how you generate targets. You kind of start with a built-in target, and then you edit it to get the specific shape you want. So the important things are that the middle mouse button kind of controls the camera, and then that you hit tab to switch between moving objects and changing the shapes of objects. Okay?
If I want to make 2 particles,
yeah.
Do I have to start with 1 and then somehow transform it into 2, or can I separately?
No, so on this create tab, for example, I just made a sphere, and I can just hit sphere again, and then I can have 2 particles here. Okay? And always, I should mention too, we put the center button because it's really useful to get everything back to the middle. So if you want to create 2, you create 2 objects here, and then under this grease pencil tab, there's a ruler, and you can measure the sizes of the things that you've made here. So we have an algorithm for that. By default, it chooses the first object that you created as the overlap. Okay, so I mean, maybe I'll just export this one quickly. This is kind of, and I'll just show you what it does. So once you've made, like, let's say these 2 objects, and then I see, for example, I have, so my polarization is here. I have 2 objects. Well, I probably don't want the polarization this way. I probably want it along the 2 objects to excite the GAC mode. So you can do this 2 ways. You can select the objects and then hit R, and then that will let you rotate the objects. And then if you hit Z, it will rotate in Z. And then if you hit Y, it'll rotate in Y. Or if you hit X, obviously it will rotate in X. And so that's kind of how you do this. And you can also, I'll say similarly, if you hit S, it lets you scale the sizes of the objects. And then if you hit Y, you can scale them, for example, in just like 1 dimension to make, these pancakes. And then so you have 2 choices to change the orientation of the object to the light. You can either click this button that says rotate the light, and then this will let you change the light polarization direction, or you can just rotate the object. It's totally up to you what you want to do. Yeah?
Okay, how do you define the situation between 2 particles? So rather you want to do 2 particles, 2 non.
Yeah, right. So that's...
Define the resolution and mesh here.
Yes, so that's what this ruler tool lets you measure distances. So you can just draw on, like, distances, for example, and measure them. And so what you'll see so right now, like, for example, this particle I need to measure, like, the distance. So, like, for example, like, this is 1.26. So the way that the mesh then is defined is in the next step. So you export this object, and then basically what I'm going to do in the second step is turn it into an array of dipoles. And so this is where it gets slightly confusing. The easiest way to define sizes, okay, because you need to define your dipole resolution as well as your space in nanometers. So the way it does this is by dipoles per unit draw space. So that's, let's say I measured that distance of 1.3. Then I use this tab, and then I can set, for example, how many dipoles are there for every 1 unit that I drew, okay?
But then it is not the same shape you want it, or the same separation when you export it from here.
No, it should be, yeah. It should be exactly, because the separation is defined by the units in the draw space. So if you, for example, if you know that, like, the separation is 1 unit, and then you set this to a value of, let's say, 10 dipoles per unit draw space, and then I set the space between dipoles as 1 nanometer, then they'll be separated by 10 nanometers. Does that make sense? So it's kind of confusing. So this is how because the problem is that you need to discretize it in terms of the number of dipoles, but you also need to define distances in that space. So you can change the scaling by changing the number of dipoles, or you can change it by changing the distances between the dipoles. But the problem is that a lot of the times to get accurate calculations, you're going to want to increase the number of dipoles just to get, because that'll give you higher resolution calculations basically. They'll be slower, but you'll get higher resolution. So if you change, for example, if I change this from 10 to 100 and I wanted to have the same dimensions in real space, I would change this to 100 and then change this to 0.1. And now the gap is still going to be 10 nanometers because it was one blender unit separation. Okay, yeah, I can tell you. But so this is the most confusing part, is how do you translate between distances you measure in your object to real space distances. But it's, you measure the distances in Blender and then you define the dipoles per unit draw space as well as the spacing between the dipoles, okay? And then you'll see here, you always want to select this one. So this is display 3D output of converted shape, because you want to make sure that the shape that you're sending to your simulation is the same as what you expected. And then as I said here, George, there's a tab for separating dielectrics for different shapes. So this will make every object have its own unique dielectric function. And then this is using inverted point allocation. So if you have overlapping shapes, you select this, and then it will remove the points from one of the objects from the areas where they overlap.
So if I want to make a core shell structure,
yes,
then I have to basically separately make the core and the shell.
you can make a sphere, and then you can make another sphere around it, and then choose inverted point allocation. So you could do that, but I will say, so you should check particularly for core shells. This is not the easiest way. There's a built-in option in DDSCAT to do core shell structures.
Yeah, I was going to say, we don't do something complicated. It's nice to know how it works.
Yeah, no, absolutely. That's what you would do. You could draw two spheres, use the inverted point allocation, and then it would remove the dipoles from the area where they overlapped. And then, again, you're going to want to say this. And then all you do is you hit convert.
And how do you define the medium around the particles? For example, if you want to do some calculation water?
Yep, you'll see that. When we send it to the calculation, you define the refractive index of the medium. Yep, so you can do it in whatever medium you want. So this is basically just generating your shape file that's going to send to DDSCAT, but you can check this target rendering, and then you can make sure that it kind of, accurately represented the shape that you wanted. And so the red will be dielectric 1 and the green will be dielectric 2. We should probably label that. Yeah, I'll say this is all a little bit, part of this is to encourage people to use this so we can get feedback to fix problems that we find, because we're really trying to expand our user base on tools like this. And so always, if you have questions like this while you're going to use the tool, you can there's a option here to submit questions and tickets, and so these will go to Prashant and Abby and me, and we'll try to answer your questions as best as we can, and we try to do this in as timely a manner as possible to help people figure out. But you can see now we've generated a pretty good representation of the object that we wanted. And then so the next thing that we do is we go to the actual DDSCAT part of the calculation. This one's a little bit slower. So you can see just because of there's a few standard built-in shapes in DDSCAT. So for example, I would say for core shell, you can just use this concentric ellipsoid built-in one, and it's easier than like drawing the things that you want in Blender probably for this particular case. But you can always import the shape that you just generated from that file convert step. And then this tab just says I'm using the light that I generated inside Blender. So I'm gonna have it be linearly polarized along that particular axis. But you can actually also, you could rotate it 90 degrees just by selecting this tab, or you could use right or left circularized or unpolarized light, which will just average the two polarizations. So then again, so I had two materials here, so I can select the dielectrics of it. We have a few supported ones, so obviously, so we have like silver, copper, and gold from the Johnson and Christie paper, the classic one, and then we also have palladium and platinum. You can also, I'll say, for people who do kind of biological stuff, you can just input a custom constant custom dielectric. This is like if you say, have a medium that doesn't really absorb, that just has some constant real refractive index, you could just input that here. Otherwise, you can just look up some scattering paper or something and look and get the measured dielectric constants and input those as X and Y values for.
You don't have soft materials?
We're totally willing to expand them. I'll say if you send us dielectric functions, we'll put them all in.
Oh, these are easy. Okay, water is 1.3. Or 1.8.
Right. So then you asked about the medium. So obviously, so those are the dielectrics of our two shapes. But here, you input your medium. And so for 1.33, this will be two spheres put together in water. Okay, and then the next step this all gets pretty simple. You just pick, for example, the wavelengths that you want to calculate it over, the number of like wavelength steps you want to take. You can go to the next step. This is where it asks you how you want to calculate the field. So you just select this, calculate the field, and you can ask for the field or the field squared, or you can ask for both the electric and magnetic fields. And then also we just added this, and I apologize, it's kind of messy right now, but this will give you a vector plot of the field directions. And this view enhancement basically just hides really weak vectors along the polarization. So you can enhance it by like, let's say a factor of 10, and then it'll hide, like the incident polarization. And then you just hit process, and then you'll see there's two options. So you can do just basically on one machine at the Purdue cluster, or you can send each specific wavelength job to a different node. And so if you're doing like a lot of wavelengths, this would speed up your calculation quite a bit, but it's actually not too bad on here. Oh, and the other thing I wanted to say is there's also a module in DDSCAT to do periodic structures, so you can array structures. It works. It's not the most efficient method for doing this. Dipole couplings tend to be pretty long range. And so this is a pretty computationally expensive way of doing arrays, but it can be done on here. And so it supports 1- and 2-dimensional arrays. And so then you just hit simulate, and it'll basically send your job off. This will probably take, a minute or two. So just in the last couple minutes I have left, I'll just show you some what the output looks like that I did earlier.
If you want to export your the job, basically take the input to the job that you're running.
Yes.
And you want to export it to a local machine, can you do that?
Yes, so always this tab here gives you an option to download whatever you're looking at. So for example, if you're looking at, you want the shape file, and you want to know what the shape file is, or you want to know what the DDSCAT parameters file that you submitted was, or something along those lines, you can always download it here through using this button here. So there's always an option to download whatever you're looking at any given step. And then also here at the end, you can access all of the go through all of the files that you made and then download them all.
I think the biggest issue we were running into is just that, we're going to want to do calculations that will always exceed what you can run.
Yeah, for arrays or for?
Arrays, a bunch of things. Okay, just seems like that 12-hour time limit is always an issue.
Oh, 12 hours? Okay, yeah. What?
You can go to take the parallel version.
Right, so it's each wavelength is a 12-hour limit. So if your wavelength takes less than 12 hours, and also you can talk to us. We have users issues about memory. Yeah, so these are all things. Yeah, sorry. Okay, so write all of this stuff down on the feedback thing, and we can petition NanoHub to change these things if it's prohibitive. Sure.
And the memory is computed automatically. Once you submit the job, we know how large is your job, and we submit it to the right cluster. So we have up to, I think, about 190 gigabytes, largest memory. Yeah, if it's remote.
Yeah. So that's pretty much it. And then you can look at the visualizations. That was a gold nanorod. Here's for example the 3D field that you output from the nanorod. Here is, I can show you what that the magnetic field, for example. It's kind of ugly in this case. The electric field vector drawings that you get, and again, you can always download any of these. And so I wouldn't say, I don't think that we're going to win you over, George. I don't think that that we're going to replace, carefully done theory like on the base. But the idea is to just let people do, quick and simple calculations that otherwise, wouldn't have access to do. Excuse me, sorry, I'm getting sick. To do them.
Oh, it looks fantastic. I think what happened was that the last time I heard, I don't remember who gave the talk to Sean or somebody, but it was maybe over a year ago, and maybe 2 years ago or something, and the code was much less capable. So.
Yeah, so we've really been working on kind of getting this stuff, up to a point where it's actually useful to people. And so, like, really, we strongly encourage everyone to give this a try, and then submit all of the problems you have, and then we'll work on fixing them as best we can. Like if you have memory issues, if you don't understand just how to use something in Blender, like any problem you have, just send it to us. Yeah, sure.
How complex a structure can you get? I mean, would you do everything with dipoles if you had nanoparticles, layered in a nanomaterial structure? Like
that would almost certainly be too computationally expensive to ever converge, yes. And similarly, if you do things with exceedingly sharp corners, like very, very small points, you can imagine you're going to have like one dipole at the point or something. You need several dipole. Typically, I think the drain and flat tile recommend having about 5 dipoles across the smallest length feature you're going to have. So very, very sharp corners are not really going to work particularly well. Now, I will say this, if you make something, you like to make it as a prism, but like these prisms tend to have somewhat rounded corners anyways, and there's methods in Blender to like smoothly curve edges and stuff like that to try to generate realistic things. So I mean, this is an example of what can be done. But I'll say, like Abby, after the other point of the NanoHub is if you guys have, like the theoretical people, if you have tools that you want to try to turn into things like this, especially if you have like some extension on DDSCAT that we could easily just add to the drain and flat tile code, for example. We had someone recently submit something that does electron energy loss simulations, so we're trying to add that. So like if you have different pieces, like as theorists, like you want to make a totally new tool or you want to upgrade an existing tool. So I'll say there is a MEP. There's a MEP tool too, but we're not in charge of it, so I don't know too much about it. So that's an FDTD-based code, and I haven't really used it too much. I don't think you can do arbitrary target geometries though in that particular code. I think but it may be better for doing arrays. You'd have to look at it. It's maintained by someone at MIT. Do you remember the name of the?
Developers.
Okay. So yeah. So with that, I think it is lunchtime.
Yes.
If you guys have questions or have, so let me just do this. If you guys have questions or comments, obviously you can submit them through the tool. Give us feedback. We definitely want feedback. Or you can email me and ask me questions. And as long as don't get way too many, I'll try as hard as I can to answer them if I know.